There has been a lot of misinformation and fear-mongering about 3I Atlas and its acceleration. Some are calling it proof of alien visitation. Others are dismissing it as just another comet doing comet things. But the truth? The truth is far more interesting than either of those extremes. In this video, we're going to explore what is actually happening with this interstellar visitor, what the data really shows, and whether we need to seriously consider explanations that make most scientists uncomfortable. Because right now, 3I Atlas is doing something that doesn't fit our models. And when the data doesn't fit the theory, we have two choices: ignore the data or question the theory. If you want to understand what's really happening beyond the clickbait and the dismissals, hit that like button now, because what I'm about to show you is based on actual NASA data and calculations from leading astrophysicists. So here's what we know for certain. Right at its closest point to the Sun, 3I Atlas started accelerating in ways that gravity alone cannot explain. NASA's Jet Propulsion Laboratory filed a report showing that 3I Atlas is 4 arcseconds away from where it's supposed to be based on pure gravitational calculations. 4 arcseconds might not sound like much. It's a tiny angle in the sky. But when you're tracking something 203 million kilometers from the Sun, that deviation translates to an enormous distance. The object is accelerating at about 0.02 millimeters per second squared. Now, that sounds incredibly small, right? Almost negligible. But here's the thing about space. Small accelerations sustained over time add up to massive deviations. Over the course of just 1 month, this tiny acceleration pushed 3I Atlas off its expected path by about 80,000 kilometers. 80,000 kilometers, that's twice the circumference of Earth. Make sure you're subscribed, because the implications of what I'm about to explain will change how you think about interstellar objects. The acceleration has two components, and this is where it gets really interesting. It's pushing away from the Sun at 135 kilometers per day squared. That works out to about 60,000 kilometers per month in the radial direction, directly away from the Sun. But that's not all. It's also moving sideways, perpendicular to the Sun, at 60 kilometers per day squared. That's another 27,000 kilometers of lateral deviation per month. So this object is not just drifting in one direction following a predictable path. It's being pushed outward and sideways simultaneously. Think about what that means. Natural gravitational forces don't create two-dimensional acceleration patterns like this. Gravity pulls in one direction toward the mass creating the gravitational field. If 3I Atlas were just being pulled by the Sun's gravity and maybe getting a gentle push from solar radiation pressure, we'd see acceleration in one primary direction, but we're seeing a two-component acceleration vector, radial and transverse. Outward and sideways. That's a pattern you'd expect from directional thrust, not from passive forces like radiation pressure or random outgassing. Now, before anyone panics and starts building bunkers, let me be clear about something important. This acceleration is not sending 3I Atlas toward Earth. The deviation is not enough to change its path toward any planet in our solar system, with one exception: Jupiter. 3I Atlas is expected to make a relatively close approach to Jupiter in March 2026. And given the acceleration we're observing, its trajectory toward Jupiter might be slightly different than originally calculated. But Earth, we're safe. This isn't a planetary defense issue, this is a scientific mystery. Drop a comment below with your thoughts, because what I'm about to explain next is where the real puzzle begins. So what exactly is non-gravitational acceleration? Let me explain it in simple terms. When you throw a ball, gravity pulls it down in a predictable parabolic path. You can calculate exactly where it will land based on the initial velocity, the angle, and Earth's gravitational pull. But imagine that ball suddenly had tiny rockets firing on it mid-flight. It would veer off course. The path would no longer match your gravitational calculations. That's what's happening here. 3I Atlas is not following the path that the Sun's gravity alone would create. Something else is pushing it. For a comet, which is what 3I Atlas is officially classified as, the natural explanation is outgassing. Here's how that works. Comets are essentially dirty snowballs. They're made of ice, rock, and dust, all clumped together. When they get close to the Sun, solar radiation heats up the surface. The ice doesn't melt, it sublimates, meaning it goes directly from solid to gas. that gas escapes from the surface, and as it does, it creates thrust, like a natural rocket engine. This is completely normal for comets. We've observed it hundreds of times. It's called the rocket effect or non-gravitational force, and it's a well-understood phenomenon. The problem, and this is a big problem, is the amount of gas that would need to be coming out of 3I Atlas to create the acceleration we're observing. And this is where things get really interesting. Harvard astronomer Avi Loeb, yes, that Avi Loeb, the controversial figure who suggested Oumuamua might be artificial, did the math. And before you dismiss him as a fringe scientist, let me remind you, he's using basic textbook physics, the kind you learn in undergraduate mechanics courses. If you know the acceleration of an object and you know its mass, you can calculate how much thrust is needed to produce that acceleration. Newton's second law, force equals mass times acceleration. From there, if you assume the thrust is coming from gas escaping the surface, you can calculate how much. Gas needs to be ejected to create that force, so let's look at the numbers. 3I Atlas weighs at least 33 billion tons. 33 billion tons. To put that in perspective, it's enormous compared to the first two interstellar objects we've detected. It's somewhere between 1,000 and 1 million times more massive than Oumuamua or Borisov. Its nucleus, the solid core of the comet, is estimated to be about 3.5 miles across, nearly 6 kilometers in diameter. That's a substantial object. We're not talking about a small chunk of ice drifting through space. This is a mountain-sized mass. Now, with that mass and the observed acceleration, the calculations show something remarkable. To create the observed push through natural outgassing, through ice sublimating and gas escaping, 3I Atlas would need to lose at least 1/6 of its entire mass during the month around its closest approach to the Sun. 1/6 of its mass. That's at least 5 to 12 billion tons of gas being ejected in the span of about 30 days. Let me repeat that because it's an astonishing number. 5 to 12 billion tons of gas. For comparison, when Mount St. Helens erupted in 1980, one of the most violent volcanic explosions in modern history, it ejected about 1 billion tons of material. 3I Atlas would need to eject 5 to 12 times that amount in 1 month, continuously. Now here's the critical part that everyone needs to understand. That amount of gas doesn't just disappear invisibly into space. When billions of tons of gas are ejected from a comet, they form what's called a coma, a massive glowing cloud around the nucleus. This coma scatters sunlight, fluoresces from solar UV radiation, and becomes incredibly bright. It would be impossible to miss with our telescopes. We're talking about a cloud that would be visible to amateur astronomers with backyard telescopes. Professional observatories would see it as clear as day. And here's where we get to test the hypothesis. Between late November 2025 and late January 2026, dozens of ground-based telescopes will be observing 3I Atlas. The Hubble Space Telescope will point its instruments at it. The James Webb Space Telescope, the most powerful observatory ever built, will analyze its spectrum in exquisite detail. On December 19th, 3I Atlas makes its closest approach to Earth at 167 million miles. If that massive gas cloud is there, if billions of tons of material are being ejected to create the observed acceleration, we're going to see it. There's no way we'll miss it. But what if we don't see it? What if the observations show only a small amount of outgassing or no visible coma at all? This is where the scientific discussion gets really compelling. If we do not see a massive gas cloud matching the amount needed to create this acceleration, then the natural explanation fails. It doesn't just become unlikely, it becomes physically impossible. If there's no cloud, then the thrust isn't coming from outgassing. It has to be coming from something else, something that can produce directional acceleration without ejecting massive amounts of visible material. And when you start listing mechanisms that can do that, the list gets very short and very uncomfortable for conventional science. If you're finding this as fascinating as I am, share this video with someone who needs to see it, because what comes next is going to challenge some fundamental assumptions. The thing is, we've seen this exact pattern before. With Oumuamua, the first confirmed interstellar object, which passed through our solar system in 2017, also showed non-gravitational acceleration. It was accelerating away from the Sun in a way that gravity alone couldn't explain. Scientists looked for outgassing. They pointed every available telescope at it, including the incredibly sensitive Spitzer Space Telescope, which can detect even tiny amounts of gas and dust. They found nothing. No visible coma, no dust tail, no gas emissions detectable by any instrument. Even Spitzer, which can detect the faint infrared glow from microscopic dust particles, came up empty. Scientists ended up calling it a dark comet, which is basically an oxymoron. The whole defining feature of a comet is its tail of gas and dust. A comet without a tail is like calling something a dry ocean or a cold fire. It's a contradiction in terms. But they had to call it something because it was clearly accelerating and clearly not showing the expected outgassing. Now, 3I Atlas is showing us something potentially even stranger than Oumuamua. It's showing two additional weird behaviours that make the natural explanation even harder to accept. First, there's the brightness issue. As 3I Atlas got closer to the Sun, its brightness increased following a power law with an exponent of -7.5. For people who don't speak math, here's what that means in plain language. Normal comets get brighter as they approach the Sun, following a power law with an exponent of about -2 to -3. That means if you cut the distance to the Sun in half, the comet gets about 4 to 8 times brighter. That's predictable, understood, and matches what we observe with solar system comets. 3I Atlas is getting bright way faster than any normal comet. It's increasing at more than double the rate we would expect. With an exponent of -7.5, cutting the distance in half makes it roughly 180 times brighter instead of just 4 to 8 times. This is completely unprecedented. No comet we've ever studied, and we've studied hundreds, shows this kind of brightness increase. Second, and this is perhaps the most visually striking anomaly, 3I Atlas is blue. Not just slightly blue-tinted. It's appearing bluer than the Sun itself at its closest approach. This is extremely weird for multiple reasons. First, dust naturally makes things look redder, not bluer. When you look at a sunset, it's red because sunlight is scattering off dust particles in the atmosphere. Dust absorbs blue light and scatters red light. If 3I Atlas were a normal comet producing dust, we'd expect it to look reddish or at least neutral in colour. Second, the surface temperature of 3I Atlas should be about 20 times colder than the Sun's surface. The Sun's surface is about 5,800 degrees Kelvin. 3I Atlas, even at perihelion, should be maybe a few hundred degrees Kelvin at most. Cold surfaces don't glow blue. They glow red or infrared. Think about heating metal. When it's cool, it's dark. Heat it a little, it glows red. Heat it more, it glows orange, then yellow, then white, then blue. Blue glow means high temperature. So why is 3I Atlas glowing blue when it should be relatively cold? The natural explanations involve ionized gases. When gas molecules are hit by intense solar UV radiation, they can become ionized. They lose electrons and become charged particles. These ionized gases can emit light at specific wavelengths, creating colors that don't correspond to temperature. Carbon dioxide ions, for example, can produce blue emissions. So it's possible, theoretically possible, that 3I Atlas has an unusually high amount of carbon dioxide sublimating from its surface, and that CO2 is being ionized by solar radiation, producing the blue glow. That's possible, but it would require a very specific composition, a very specific geometry of gas emission, and very specific solar illumination conditions. It's not impossible, but it's adding another layer of this has to be just right explanations on top of all the other anomalies. Now, it's important to understand what is actually being argued here. Scientists like Avi Loeb are not declaring that 3I Atlas is definitely alien technology. They're not saying this is a probe or this is artificial with certainty. What they're saying is more nuanced and more important. The argument is about scientific methodology. When you have data that doesn't fit your theories, you don't get to just dismiss the data. You don't get to say, well, it must be outgassing even though we can't see the gas, because what else could it be? You have to take the data seriously and explore all possible explanations, even the uncomfortable ones. Loeb gave an example from a Harvard lunch where he was talking to young astrophysicists about something called the Hubble tension. That's a technical name for a real problem in cosmology. Different ways of measuring how fast the universe is expanding give different answers. When you measure the expansion rate using distant supernovae, you get one number. When you measure it using the cosmic microwave background radiation, you get a different number. The two methods should agree. They don't. Some scientists were saying the data must be wrong because they couldn't explain the discrepancy with current theory. Loeb told them that's terrible science. You don't get to say the data is wrong just because you don't have a theory that fits it. The data is what the data is. If your theory doesn't explain the data, you need a better theory, not an excuse to ignore the measurements. And that's exactly the situation we're in with 3i Atlas. We have measurements, real, verified, NASA-certified measurements showing acceleration that doesn't match gravitational predictions. We have observations showing unusual brightness increases, blue coloration, and behavior that doesn't fit standard comet models. We can either assume it's all explainable by natural processes we just haven't modeled correctly yet, and wait for better observations to confirm the conventional explanation. Or we can acknowledge that the data is weird enough that we should seriously consider alternative hypotheses, including technological explanations and design observations specifically to test those hypotheses. The first option is the comfortable choice. It's the one that doesn't ruffle feathers or invite mockery. The second option is the scientific choice. It's the one that follows the evidence wherever it leads. Here's what we're going to find out in the coming weeks. If 3i Atlas shows a massive bright coma with billions of tons of gas streaming off it, then great. The natural explanation holds. It's just a weird comet with unusual composition, and we'll learn something new about interstellar objects. But if we don't see that coma, if the observations show only minimal outgassing that can't account for the acceleration, then we have a problem. Then we're left with an object that's accelerating without visible means of propulsion, an object that's glowing blue when it should be glowing red, an object that's brightening far faster than any comet should, an object that's exhibiting two-component acceleration, radial and transverse, in a pattern that looks more like controlled maneuvering than random outgassing. At that point, the technological hypothesis stops being fringe speculation and becomes a legitimate scientific possibility that deserves serious investigation. And here's the really interesting part. We have the tools to investigate this properly. The James Webb Space Telescope can analyze the chemical composition in exquisite detail. If there's unusual isotopic ratios or elements that don't match natural comet formation, we'll see it. Radio telescopes can listen for any electromagnetic emissions. If there's any signal, any modulation, any pattern, we'll detect it. The Juno spacecraft will be near Jupiter when 3i Atlas makes its approach in March 2026. Juno has instruments that can detect electromagnetic activity. We're not helpless here. We're not just speculating in the dark. We have the capability to gather the data needed to distinguish between natural and artificial explanations. The question is, do we have the courage to look? Do we have the scientific integrity to follow the data even if it leads us to uncomfortable conclusions? Or are we going to do what Loeb's colleagues at that Harvard lunch were doing, dismissing data we can't explain because it doesn't fit our comfortable worldview? I want to be clear about something. I'm not saying 3i Atlas is definitely artificial. I'm not claiming aliens are visiting us. What I'm saying is that the data is genuinely anomalous. The behavior doesn't fit standard models. And when that happens, we owe it to ourselves, to science, to humanity, to investigate thoroughly rather than dismissing it with hand-waving explanations. History is full of examples where scientists dismissed anomalous data because it didn't fit existing theories. Continental drift was dismissed for decades because geologists couldn't explain how continents could move. Meteorites were dismissed as impossible because stones don't fall from the sky. Ball lightning was considered folklore until we had enough documentation to take it seriously. The lesson from history is clear. When you have good data showing something unexpected, pay attention. Don't dismiss it. Investigate it. So what do we do now? We watch, we observe, we analyze. December 19th is going to be critical. That's when 3i Atlas makes its closest approach to Earth and when we'll have our best opportunity to observe it in detail. If we see a massive coma, the mystery is largely solved. Unusual comet, but still a comet. If we don't, if the acceleration continues without corresponding outgassing, then we're in completely new territory. then we'll need to seriously consider that we're looking at something that challenges our assumptions about what's possible in nature. And that would be the most exciting scientific discovery in generations. If you found this analysis compelling, smash that like button and subscribe for updates as this story develops. Drop your thoughts in the comments. Do you think 3I Atlas is just a weird comet, or is there something more going on? Share this video with someone who's fascinated by cosmic mysteries. Because right now we're living through one of the most interesting astronomical events in modern history. An interstellar visitor is behaving in ways we can't fully explain. We have the tools to investigate it properly. And in the coming weeks, we're going to get answers. Whether those answers fit comfortably into our existing worldview or force us to expand our understanding of what's possible, that's what makes this so exciting. The universe is speaking to us through this object. The question is, are we listening? Thanks for watching, and I'll see you in the next one.